This image gives a complete and easy-to-understand explanation of an ideal operational amplifier, commonly called an ideal op-amp, which is a very important component in electrical and electronic circuits. An op-amp is basically a high-gain voltage amplifier that takes the difference between two input voltages and amplifies it to produce a much larger output voltage. These two input terminals are labeled as V1, which is the inverting input, and V2, which is the non-inverting input. The output voltage, shown as VO, is calculated using the formula VO equals A times VD, where A is the open-loop gain of the amplifier and VD is the voltage difference between the two inputs, V2 minus V1. In an ideal op-amp, the gain A is considered to be infinite, which means that even the tiniest voltage difference between the inputs can generate a very large output voltage. But in practical circuits, we use negative feedback to control this gain and make the amplifier work in a stable way. Because of the high gain and negative feedback, the voltage at the inverting and non-inverting terminals becomes equal, meaning V1 equals V2, and the differential input voltage becomes zero. Another important characteristic is the input resistance. An ideal op-amp has infinite input resistance, which means it does not draw any current from the input sources. This is why both input currents I1 and I2 are zero, as shown in the diagram. On the other hand, the output resistance of an ideal op-amp is zero, so it can supply full output voltage to the load without any internal voltage drop or power loss. The bandwidth of an ideal op-amp is infinite, which means it can amplify signals of all frequencies without distortion, whether they are low-frequency or high-frequency signals. Also, the offset voltage, which is the small voltage needed between the input terminals to make the output zero, is also considered to be zero in an ideal case. The left part of the image shows the internal equivalent circuit of a non-ideal op-amp, where you can see the input resistance Re, the output resistance Rho, and the dependent voltage source A times Vd, all arranged inside the triangular amplifier symbol. The image also highlights that input resistance should be high to avoid loading the signal source, and output resistance should be low to deliver power efficiently to the load. The right part of the image shows the symbolic representation of the ideal op-amp model with directions of input and output currents. It shows that I1 and I2 are both zero, and the output current I0 is the sum of all currents flowing from the amplifier to the load. It also shows the essential rule that V1 equals V2 due to negative feedback in ideal operation. Finally, the table summarizes the key properties of an ideal op-amp: infinite open-loop gain, infinite input resistance, zero output resistance, infinite bandwidth, and zero offset voltage. These ideal conditions make analysis and design of amplifier circuits much easier, even though real-world op-amps can only come close to these ideal values.